In this video, we're going to discuss distributions and how we describe them. Particularly, we're going to focus on the standard deviation, which is a good reference number that helps you decide the effectiveness of your treatments and how far an individual observation or patient, in your case, is different from normal. So let's start off looking at the Beaver Dam Study. Beaver Dam is a little town in Wisconsin, and they gave everyone over 50 an eye examination. And they were interested in the distribution of glaucoma and the relationship between glaucoma and IOP and intraocular pressure and other things as well. So here's a distribution of those IOPs, the percent of people. These are observations, all of the people in the town and what their distribution looked like. Now, about 2% of the people have glaucoma. If we look at this graph, it looks like the distribution is skewed because it looks like it's trailing off to the right. But if we look more carefully, we can see that in these three bars contain 10.3 plus 3.9 plus 0.8, or about 15% of the cases. Over here, this one bar has 18%. So it's kind of a little bit of an unfair graph in looking at what the distribution is. I believe it's probably more symmetrical than it appears. Now I simulated the data and presented these graphs of distributions based on the Beaver Dam study. And this red line is the normal people, and the blue is the those who have glaucoma. And we actually adjusted for taking eye drops and kind of lowered the mean for that. But if this line coming right up here is 22, and from the slide before, we noticed that at 22, you are about 95% of the people, maybe a little more, have an IOP less than that. So if you were out here someplace, we could reject the notion that you were probably had normal IOP. What we can't do, though, is if you're in here, reject the notion that you are disease-free from glaucoma. Because as we look at this graph, and again, the line, and I've taken a log transformation here to make this tiny little bump look a little bit bigger so that we can see things a little better. But 22 is our cutoff. You can see over here 22. You have this space in here which says if you have a person that say their glaucomas or their IOPs at 23, well, there's a better chance they're going to be normal than they are who have glaucoma. And you can also see that there's a lot of people less, all these people in here, who are less, the proportion of the glaucoma patients who are less than 22. And so it's misleading, as I said, and you must avoid this typical rule of if it's less than 90%, assuming the person is okay. Whereas you can say if they're out here greater than 95 percentile, you can say, well, they are probably hypertensive anyway. They're not normal. Now, the way we describe these distributions is to talk about the mean and the standard deviation. The standard deviation is a measure of variance and of variability, and here's the formula. Now let's break this down. First, let's start with the mean, the sum of x over n. We have data points over here. The numbers, the observation, the first one was 1, then 2, then 3, then 4, then 5. This isn't I could have said 5, 4, 3, 2, 1 and gotten the same thing. It's not the ID number, it's the data point. And the mean of these 5 numbers is 3. We sum them, 1, 2, 3, 4, 5, that's 15. Divide by n, that's 5, and we get 3. Now, that's just a single point. That doesn't tell us much about the distribution other than where the center is. And we want to know about the variability of the distribution. So there are a lot of differences between distributions if we look at them. So here we have x, up here we have the sum of x, here we have the sum of x minus the mean. So the deviation is the amount of difference between each value and its mean. When we sum all of these up, as we've done over here, we have 1 minus 3, 2 minus 3, 3 minus 3. These are all these data points minus 3. The sum is 0. The sum is always 0. No matter what your numbers, 1, 2, 3, 4, 100, the sum is going to be 0 as long as it's from the mean. Now, if this was 1, 2, 3, 4, 100, the mean wouldn't be 3, it would be something else. And when you added them all up, you would get 0. Now, so the positives and negatives balance. So one way to get around that is to square it, because squaring a negative gets rid of it. So minus 2 squared is 4, 1, 0, 1, 4, and the sum of those is 10. So the sum of x minus mean, that squared, that's 10, and then we want to get the average, so we divide by n. That's called the variance. It's population variance. But now we've done a sample, we haven't measured everybody out in the population. We never do. So we have a sample deviation. We subtract 1. Makes the standard deviation a little bit bigger. It compensates for the fact that our sample probably doesn't get the true breadth of the population. But note that the larger the sample, the less that 1 is effective. So our sums of squares is 10 divided by 5 minus 1 is 2.5. But now that's a squared deviation. We want the actual deviation, so we take the square root. And we call that the standard deviation. And that, in this case, is 1.58. And we know that between, we know that plus or minus 2 standard deviations is usually 95%. Plus or minus, the observations fall within that. 68% fall within plus or minus 1 standard deviation. And if we go out to the 99.8 percentile, we'll grab about 99.8% of the observations. Now, the thing that's interesting about this is true no matter what the observations are. I just wanted to briefly touch on the brief that we have given, that little outline. There's a second page, and it has a bunch of measures that were taken from a sample of 356 ortho-K patients. And this is the difference, like 39.39, is the difference when you take that range and divide by 4, and you subtract it from the actual standard deviation, 1.2. If you divide that range by 5, the difference is 0.11. The purpose of this is kind of showing you, as you go down that page, all the yellows are either 5 or 6 standard deviations. And in other words, even though all these measures are very different, they all are about the same number of standard deviations wide, between 5 and 6. And that's very useful, because when we say a 1 standard deviation is different in, say, age, that's equivalent to a 1 standard deviation in sphere. Now, this relationship doesn't actually work very well if the distribution is spherical. It's different 1.46. The standard deviation is 72. So it's a lot bigger in this estimation. So this works with symmetrical distributions, not necessarily bell-shaped ones, but symmetrical. And if you look at this dotted line, that's the 95th percentile. And you can see that, or that's 2 standard deviations, and that's about the 95th percentile. So standard deviation works okay with the percentiles. It just doesn't work that well with the actual standard deviation. So the reason the standard deviation and this concept that everybody is the same is so important is because it lets us calculate something called effect size. An effect size, it helps you in interpreting papers because a 0.5 standard deviation difference is the same no matter what has the same meaning no matter what you're measuring. It's in relation to the entire distribution of the particular measure, a half standard deviation is pretty much the same because we know standard deviations cover between 5 and 6. There are 5 and between minimum and maximum, there's about 5 to 6 standard deviations. So this effect size is the mean of group. Now this effect size is in terms of means. And when you have a mean of group A and a mean of group B, the difference divided by its standard deviation is the difference in standard deviation units. And we can see when we're talking about means, we have this effect size of 0.5. Now, 0.5 is, arbitrarily speaking, is about the point at which a patient can clinically notice a difference. So if the difference between one pair of glasses and another pair of glasses, the patient's ability to see something, their acuity, they will notice the difference between the glasses if it's greater than 0.5 standard deviation difference between those two means divided by the average standard deviation. And that's very useful. The same way with if you give a drop, you have 2 drops, and the IOP is lowered, and the difference is greater than a 0.5 standard deviation. Actually, it's probably not a good example because people don't really notice their IOP and symptoms. So we think of something else, dry eye. So if you were doing 2 drops, and one had on a dry eye symptom scale, they were a half standard deviation better. The person would notice their eyes were a little less dry with 1 drop over the other. Now this is a minimal clinically relevant difference. You really want the differences to be bigger than that in order to have a substantial effect size. Now this reflects back to my example that I gave in the literature review. And this is the impact of this blue light filtering glass on computer vision syndrome in radiology residents. Radiologists spend their day in a dark room with big giant monitors, computer monitors, looking to see differences in things. And they're subjected to really quite intense amounts of blue light. So the question was, can we give these glasses and will it help? And the way they measured it was through symptom surveys. They had a computer vision syndrome, a Swedish occupational fatigue one, and they did a randomized prospective crossover study. So this isn't a bad study in terms of its design. Remember that a crossover study is one in which you have your sample and you randomize people to one group or the other. One group wears the blue blocking lenses first, and then a sham pair, a clear pair the next week. They wore them for 1 week each. Whereas the other group wears the sham first, and then the blue blocking glass. And they concluded that the blue blocking lenses may relieve some CVS symptoms. Now, the thing I liked about this paper was they gave us a lot of cases where we had means and standard deviation. These are the two pairs of glasses, and I can't tell you which is which without looking at the labels. So they're both pretty clear. And so the scales, this talks about the scales, different things. Here's a problem with this study. Now, in all fairness, they labeled it a pilot study. There are 10 residents, 4 males, 6 females. That is a pathetically small sample, which is fine if you're doing a pilot study, but really you shouldn't be publishing pilot studies. They're to test feasibility, and this is just setting people up. So we have our results. These we see the mean and standard deviation for the blue blockers, mean and standard deviation for non-blue blockers. We give p-values over here, which we'll consider in a later video, but none of them are significant or even in the range of near range of being significant. The same way with the SOPI test. Now, this test up here, they're talking mostly about eyes and things that happen with eyes. In the SOPI questionnaire, it's more about lack of energy, worn out, not eyes specifically, sleepiness, falling asleep, drowsy, just kind of your alertness. And again, they have, in terms of p-values, there's nothing in the neighborhood of significance. Now, to a certain extent, you wouldn't expect that because they only had 10 subjects. And so you're not going to get very significant p-values unless the difference are really huge. And so let's take a look at the differences. So what I did was I went in and copied their table. Here's the SOPI. There's the mean of the blue blockers, the mean of the non-blue blockers, the standard deviation. The difference between these two means, the 2.58, 2.97. And you take the treatment and subtract the control and you get a minus 0.39. Then the average deviation, 2.28, 2.97, is 2.29. So you divide minus 0.39 by 2.29 and you get a minus 0.17. Now this is the effect size that if it's clinically relevant in terms of can the patient notice a difference, you want that number to be at a very minimum greater than 0.5. And you go down here and you see that just isn't the case. There are no effect sizes that are greater than 0.5. Now, effect size is not a function of sample size. So that lack of clinical relevance isn't due to the fact they didn't run enough subjects. Effect size doesn't get bigger or smaller the more you run. It just gets more accurate. It could go either way, but it would be more accurate if they had run 100 subjects instead of 10. But it still may or may not be significant. So there was really the same thing. Eye symptoms. We can look through here. We can see for burning, the mean of the blockers is 154. The mean of the non-blockers is 1.56. Standard deviation, the average is between 92 and 94. 93, the average is 93. 0.02 divided by 0.93, that's almost 1, is minus 0.02. Now the authors make a big deal that most, and by most I mean just a little bit over, about 2/3 are negative, meaning that the blue blockers were better. That was true with both the CVS and this. So rather than looking at effect size, they looked at the proportion that was greater, that gave them their conclusion. So I like this study because it gives us and it enables us to look at the effect size, notice they don't calculate it. This is something that you really need to do every time you read a paper. You have to figure out how to compute the effect size, because the effect size gives you this sense of clinical relevance. And you want to know if the difference is clinically relevant. These differences are all trivial. And so you would not, even though it says that it may ameliorate, well, I mean, there's maybe enough evidence here to run a larger study, but there is definitely no change in practice suggested by these studies. I would not recommend blue blockers based on this. So in summary, we've learned that distributions come in all shapes and sizes. The standard deviation is a standard reference for differences. When we talk about observations, 68% fall within plus or minus 1 standard deviation, 95% fall within plus or minus 2 standard deviations, and 99.8% fall within 3 standard deviations. When we talk about individual means, or group mean, when we talk about comparison of group means, 1/2 standard deviation between the two means is noticeable by a subject and probably could be considered a minimally clinically relevant difference. Less than 0.2 standard deviation difference, effect size less than 0.2, is pretty trivial and likely to change if you really see.